like instance deriving arbitrary for your data types. Of course, that's not the syntax, it's more of a splice. But yeah, it uses template Haskell and does what you might expect. So it goes through the structure of the data type and generates arbitrary instances. Currently, it's very naive in the way it does this. So it's basically what we would find in some tutorial of how to write arbitrary instances. But you know, we could eventually make it much more interesting. So here's an example. So this is an example from the Juicy Pixels library, which is a library for image manipulation. And of course, it has a support for lots of file formats. One of them is GIF file. So there's this type that represents the GIF header and with images and something called the looping behavior, just when you have little animations in your GIF file. The point is that there's some encoding into Haskell algebraic data types of the structure of a GIF file. And we have lots of files, like lots of types, not just one. It's just, there's a separate type for GIF headers and there's a separate type for this GIF image stuff and stuff like that. But what we get through Megadeth is an instance that is pretty much like what we would expect. We use the size parameter in the gen monad to just very simply take the constructors and recursively generate arbitrary elements of the fields in the constructor. So it's just very much type directed. And note that in this example, we also need to recursively generate instances for the types that are somehow nested in this GIF file representation. And we also do that, so we also go through and we will get an instance of arbitrary for GIF header and an instance of arbitrary for graphic control extension, GIF image, GIF looping. These are all separate types that need separate instances. So we will get all those. And Megadeth actually supports pretty much anything you might imagine in terms of Haskell 2010 algebraic data types. So no weird extensions are supported. And yeah, it also supports, for example, mutually recursive types. It's not very hard. It's just a matter of writing it, finding all the instances and generating them. So this is sort of the more elaborate pipeline that we have for QuickFuzz. So we have this extra step before that generates the arbitrary instances that we're going to use. We call that Megadeth, and then we feed that to the previous pipeline that I explained, and I added some things here. So to the right, we have this file shrinking step, pretty much like we are used to in QuickCheck. We can shrink our failing test cases to get nicer test cases, and we currently use a very simple heuristic for shrinking. So we just take prefixes and suffixes of the byte strings that cause these programs to fail. But this has surprisingly been quite successful. So these are all the file types that we currently support, which is quite a lot. And we heard stuff from the fuzzing community. They were very happy that apparently this is the only tool that supports all of these things out of the box. And the reason we have, I don't even understand some of those. So the reason we can support all this is we just take the types from Hackage libraries. So big thanks go to library authors that upload things in Hackage and allow this to happen. We have some performance numbers here. So these graphs are basically a simple test that we did using generating and fuzzing formats like zip, PNG, and SVG. So this is an archive format, an image format, and SVG is kind of an image, but it's much more structured. It's kind of a markup format as well. And we see the bars to the left are the time that it takes to generate these things. And then the second bar is just generating and executing the program. So we can sort of see here that there's not that much overhead in generation, except for SVG, there's significant overhead, but that's sort of to be expected, and our arbitrary instances are not very clever about it, so it makes sense that there's a lot of inefficiency there. And the other two bars are the mutations, so it's the whole thing. It's also doing the mutation step with two different fuzzers. And it's interesting that the results are not stable among fuzzers even, because we see that for zip and PNG, a fuzzer called ZSUF, which basically just goes ahead and changes bits in the byte strings randomly. Those are sort of much more. They take much more time than using a sort of more specialized fuzzer called Radamsa, which looks at the structure of the file and tries to do something more clever about the mutation. But we see that for SVG, this is much more expensive, so Radamsa sort of takes more time. Anyway, so we found lots of bugs and crashes that were previously undiscovered. So if you look at the paper, all the bugs in the paper are basically 0-day bugs. So they were all completely new bugs. And we found bugs in all these things. In particular, we found, so the initial example is actually true. We actually found a bug in GDK, which causes this behavior where you can cause a buffer overflow and use that to construct an exploit that will allow you to run arbitrary code. Well, now this has been patched, of course, but we even got a bounty from Mozilla for that. So yeah. As for future work, so we have basically these two levels of fuzzing. We have low-level fuzzing and high-level fuzzing, but we can also think of fuzzing at different levels of abstraction, not just either generating bogus files from imprecise types, or changing bits down in input, but lots of things in between. And the interesting thing, I think, is that all of these file formats have some invariance, and it would be interesting to find ways of systematically exploring different test cases where we maybe break one of the invariants, then break the other one, and so on and so forth, and find all combinations of those, sort of focusing more on the structure. Because currently, just changing random bits, if you think of a big image, there's a chance we might just be changing one color, so that's not very interesting. That doesn't really exercise whatever the program is supposed to be doing when reading the structure of the file, but rather just changing something that looks more like a value. Yeah. And the last bit there, pretty printing library. We also thought that it might be interesting to basically have a way of letting programmers annotate their pretty printers. And so I call them pretty printers, but it's basically the serialization function. So there's always some way of linearizing these things. We have some representation of a file format, and then we want to write it as a file. So there's always some function that converts it into a string somehow. And in this function, many invariants are sometimes encoded sort of in an ad hoc way. So if we could provide a library to express these things explicitly, then we could maybe run the pretty printer in a mode where we can get the broken invariants sometimes, and like having a production mode and not production mode, and yeah, something like that. I'm running out of time. So to sum up, we've introduced QuickFuzz. It's an automatic out-of-the-box fuzzer that supports lots of file formats. It's basically a combination of borrowing hackage types and using QuickCheck and a bit-level mutation fuzzer. We have Megadeth, which supplies missing arbitrary instances, and sometimes not just missing instances, but basically we don't trust instances that might be included in libraries. So in general, we use the ones generated by Megadeth. And it is black box because we're generating files. So as long as you have a program or a library that's supposed to work with a given file format, we can test it. So it's not limited to Haskell programs. So yeah, that's it. Please check out the website for the project, quickfuzz.org. We're also looking for contributors. We have a few already. It's an open source project, and there's a GitHub page and so on. So if you're interested, do check it out. And that's all I have. Thank you.
Okay, we have time for some questions.
Hey, John Launchbury, DARPA. When you're doing the fuzzing, where is most of your time going? Is it in the execution, or is it in the generation of the variants, or what?
It's, I would guess it depends. So we can go back to this. So normally it's in the execution. But in things like, for example, mutating SVGs, certain fuzzers take a long time because they try to do clever things with the format. So they go in and look at the structure and so on. That's why. Well, so we don't have our own fuzzer. We just take off-the-shelf fuzzers and combine them with. So yeah, so either it's usually running with ZZUF or Radamsa. Yep.
So if I make an analogy with compiler testing, if you generate random strings, then you're going to be very good at provoking errors in the lexical analyzer, and
yes.
Vulnerabilities there will be easy to expose, but vulnerabilities in the people optimizer will be very hard to reach. I wonder whether the same kind of effect may occur in this context. And one way to know or to perhaps suspect that it's happening is if you look at the coverage that you achieve of the software that you're testing. I'm wondering if you've taken a look at that.
We haven't, but that's a good point, yes. We sort of suspect that is the case, and that's why we have as future work we want to look at ways of finding these invariants and breaking them systematically, because we know that we're just sort of barely scratching the surface, so to speak. Yeah.
Thank you. You mentioned a bunch of fuzzers that I've heard about but not used, and you didn't mention the fuzzer that I actually have a lot of experience with, which is American Fuzzy Lop.
Right.
And I mean, the particular thing about American Fuzzy Lop is that it instruments the code, the code under test, and then it uses feedback from the runs instrumentation to then guide the fuzzing. Can you compare and contrast what you expect to be the difference between those two approaches are?
I can try. So it's very hard to compare fuzzers because we found things that other fuzzers didn't find, but the same holds for the other way around. The approach is kind of different, so we can't use it directly because what we need is a function. Is basically something that acts like a function from byte strings to byte strings. So that's why we use the ones. So these two. And Hong Fuzz also works like that. That's as much as I can say. I don't know. Yeah.
With regards to getting specifications from data types on hackage, how do you, if multiple packages define a similar data type for a same file format, do you do it for all of them?
No, so this is sort of curated. We selected the packages, yes. And it's relatively easy to extend QuickFuzz with new formats if you want to.
So for different file formats, different parts of the generated bit string are more vulnerable than others. For images, the middle isn't very interesting because you're just mutating the image, but the header is very vulnerable. So do you have some kind of heuristic that influences where the fuzzing in the file actually happens, depending on the file type?
Not yet, no. So it just.
Are you planning to integrate something like that?
Yes, that would be good to add, but it's still sort of work in progress. So this is the very naive approach. And it's still giving good results. I was frankly quite surprised.
Okay, thank you.
Did you find any bugs using just a high-level fuzzing?
Yes, we did find a few, yes. Sometimes you don't need the mutation fuzzer.
So I had one question over here. Hi. So what you do now is a lot of bit-level fuzzing. I think it'd be really cool if you would look at fuzzing at a more high level, right? Because you have these data types.
Yep.
As soon as you have coproducts in there, you can kind of choose different subtrees and try to break things in that way. And that might be a good way to get to what John was saying, where you want to kind of break things in more interesting ways.
Yes, I totally agree. Yes.
Cool. Very nice.
Yes.
Joachim Breitner, Philadelphia. In your list of broken applications, I didn't see any Haskell programs. Did you not find any there, or did you not look for bugs there?
We didn't look for bugs there, actually. Or maybe we did. Yeah. So these are the major ones. These are not the only ones. So you can check the website. I don't keep track of everything now because there's lots of people involved.
Okay, let's thank Pablo again.
Thank you.
Okay, now we have